The unreasonable effectiveness of discrete-time Gaussian process mixtures for robot policy learning. Current policy learning methods, like diffusion policy, are slow, compute-heavy, and require many demonstrations. At the same time, they are brittle and hard to update at inference time. We present MIDI-Gap, a new approach that learns complex, multimodal, and long-horizon tasks from as few as 5 demonstrations. It generalizes widely across task environments and object instances and trains in under a minute on a standard CPU. MIDI-Gap supports efficient inference time updates, for instance performing a learned task while avoiding novel obstacles, or generalizing across different robot embodiments. Its speed, expressiveness, and interpretability enable dynamic tasks like scooping up an object or preparing pour-over coffee. So, how does it work? MIDI-Gap is an object-centric multi-stream method modeling the end-effector trajectory distribution in multiple local coordinate frames. For example, in both the robot's initial frame and an object's frame such as the microwave doors. These frames are automatically identified from visual input. At inference time, these local models are composed into a global Gaussian policy. By leveraging discrete-time Gaussian processes, MIDI-Gap captures fine-grained, constrained motions with high fidelity. Traditional methods like GMMs lack this expressivity. MIDI-Gap also learns multimodal trajectory distributions from limited data. First, it discovers modes in the data using lightweight tools like Riemannian k-means. Then it fits a mixture of discrete-time Gaussian processes, hence the name MIDI-Gap. Because MIDI-Gap predicts full trajectory distributions, we can update it at inference time using new information. Either to rule out infeasible modes, here one leading to collision, or to refine the predictions using constrained Gaussian updates. Here again, to avoid obstacles while still completing the learned task. Finally, MIDI-Gap also generalizes across robot embodiments. Rather than naively executing a policy learned for a different robot, which can lead to kinematic singularities, we optimize the new robot's joint trajectory to maximize its likelihood under the predicted trajectory distribution. This variance-aware path optimization ensures both task success and kinematic feasibility. Our real-world experiments leverage 2 perceptual systems. For most mildly constrained tasks, we automatically extract task parameters using dyno keypoints. For the pick-and-place task and all highly constrained tasks, we use foundation pose. Later, we highlight the generalization capabilities enabled by each system. Both perceptual pipelines support robust object localization, enabling consistent policy execution. MIDI-Gap learns even long-horizon, high-precision tasks like coffee making from just 5 demonstrations. However, while both coffee making and bread preparation involve long action sequences, their structure remains mildly constrained, with largely free space motion between contacts. In contrast, tasks like opening a cabinet door are highly constrained, requiring precise motion paths. Unlike TAPAS-GMM or key pose-based methods like ARP, MIDI-Gap excels even in those tightly constrained settings, opening doors or wiping surfaces. This level of fidelity and expressivity also enables dynamic tasks, such as scooping objects with a spatula. Another key strength is MIDI-Gap's interpretability, which fosters trust and ensures safety, critical when executing such dynamic motions on real hardware. As shown here, MIDI-Gap also demonstrates robustness in delicate tasks like water pouring. Bringing together sample efficiency, robust scaling to long horizons, high-fidelity manipulation, and safe and dynamic execution allows MIDI-Gap to learn difficult tasks like the spiral pouring task in mere minutes. Here you can see how MIDI-Gap's dense trajectory modeling leads to greater fidelity in policy learning and to smoother movements compared to TAPAS-GMM. We study visual generalization using 2 tasks. For pour drink, we rely on dyno keypoints, which generalize across environments, clutter, and even object instances, as illustrated by varying cans, bottles, cups, and mugs. For this pick-and-place task, Foundation Pose provides robustness across clutter and environmental variation, though not across object instances. Finally, we demonstrate MIDI-Gap's ability to adapt at inference time. In this multimodal pick-and-place task, for instance, a banana can be placed in either mug for task success. By incorporating collision constraints at inference time, we guide MIDI-Gap to avoid newly introduced clutter while still completing the task. We applied the same principle in this open draw task, selecting a feasible draw path that avoids obstacles while ensuring task completion. Thank you for your attention. Code and datasets will be available for download on our website soon.